Okay, so now I'm recording, and we're going to get started here with our experiment today. We're going to be doing nitration of bromobenzene, and once again, this is all together. Usually it would be 2 class periods because we have to wait for things to dry, etc. But since we don't have to worry about the time constraint, we're just going to go forward here as it's a one-day experiment. So firstly, what we're going to be focusing on here, electrophilic aromatic substitution. That is going to be the mechanism pathway that we're going to be utilizing in order to nitrate the bromobenzene. So we're talking about utilization of an arene or sort of aromatic group attached with a proton or any sort of situation where we have an electrophile that is going to substitute our arene, which is an aromatic compound. And so the big things here to know from our vocabulary: aromatic, AR is shorthand for aromatic, and arene, same situation. And then E plus is going to be an electrophile. So it desires electrons, right? So who is going to provide the electrons? The aromatic compound, very, very has a lot of electrons, sort of nucleophilic in a sense. The electrophile is going to seek it as a source of electrons, a very large source of electrons with a lot of pi bonds, and allows us to donate out our electrons to the electrophile. And so, they say here this is oversimplified because usually it's generated during the reaction, and a Lewis base would assist in the removal of a proton. So coming forward here, this is just the general mechanism. The rate of electrophilic aromatic substitutions are going to be second order. So if you need to know that in terms of your kinetics, that's good to know. Not too relevant with what we're going to be performing in terms of the reaction itself. And the first order in the aromatic component and electrophiles. So together, you put the two together and get your second order overall. This would be the rate law if you needed to know it for physical chemistry. The formation, however, of a nucleophile, the formation of an electrophile here is by the utilization of a catalyst. So whenever we utilize this catalyst in a homogeneous situation here, then what happens is that in equilibrium, the electrons can actually donate over to the nucleophile and separate it from the electrophile. Then what happens is that the reaction with the electrophile happens here, where that our arene is going to be the rate determining step of the electrophile attaching to the arene, and it has a partial positive charge. And of course, you should know that the brackets means that this is an intermediate, right? So in the intermediate, this is the fast step. So these are the two portions that we need to know of the second order reaction, followed by the fast step of the proton leaving the system and the electrons that are attached to the proton binding over to the proton. So the electrophile is usually produced by the reaction, like we discussed up there. This walks through the explanation of it. If you need to know any further ideas going forward towards it, this is bimolecular. And the reason that it is bimolecular is because that it has a rate determining step here binding in the electrophile and then in the fast mechanism afterwards of the proton leaving. This would be considered an Se2. So you may know of SN2 from organic chemistry 1 with the more simple reactions. This is a substitution electrophilic bimolecular 2 reaction. Experiments involving 4 different reactions, such as are given, and then so these are other reactions that are common, such as the Friedel-Crafts alkylation, acylation, nitration, and bromination. But today we're going to be talking about nitration of bromobenzene. So this was just the theory behind it and the sort of mechanism pathway that we would be following through. In this case, too, we do have an intermediate action for us to be able to actually nitrate it. Utilizing our catalyst in this system would be sulfuric acid. And the reason that that would be is because we have an electrophilic species known as the nitronium ion, NO2+, produced by the reaction of sulfuric acid with nitric acid. So what happens is that the sulfuric acid protonates the nitric acid, creating the nitronium ion because water can leave the system. And we'll go forward to look at the mechanism on Google afterwards if it's not provided down below. So that way that you can see a good detailed mechanism. I would assume that the lab manual would request you to go forward to provide a mechanism, so we can cover that as well. And so nitric acid is the weaker of the two strong amino acids, so it's actually serving as a base, which is very strange in the system, but you can take it as it is the electrophile, and the Aryan is wanting to attack that and then go away with the proton, creating water in the system. So the rate determining step, RDS, involves the nucleophilic attack of the aromatic ring, which is a Lewis base, on the nitronium ion. So like I said before, the arine is attacking. So think of this benzene ring attacking the nitronium ion. Then in the final step, a base such as water can act as a base and pull off a proton and create acid in the environment, or bisulfate can deprotonate the complex in order to regenerate the aromatic ring from the start. And so, like they said here, they don't really want to explain the mechanism. So I will pull up the mechanism for you afterwards on Google, and when we will look at it together. And so the mechanism of a nitronium ion with a substituted benzene, so bromobenzene, is similar to that with benzene. However, there can be 3 different products that can be formed because of the presence of the bromine ion. And if somebody who has their microphone on can mute himself right now, then we can continue forward. Here we go, I'll just do it for you. Now, however, the 3 different products can now be formed because of the presence of the bromine atom on the ring. The activation energies for the attacks in the positions ortho and para to the substituent are lower than that for the attack of the meta position. And the reasoning why that you should know from organic chemistry is due to a couple things, right? So sterics, and also what is bromobenzene? Is it an activating group or is it a deactivating group? And that will be another portion that we can cover within the mechanism as to why it would prefer to attack meta. Thus, like an alkyl group, a bromine ion example of an orthopara director, since it favors these the formation of these isomers over the meta. And they say the nitration reaction, the preference is about 100 to 1. So that would be why here, because they say like an alkyl group, the bromine is an example orthopara director. And so that can explain forward going as to if we had percentages here of each portion and how we would be extracting that going forward into the actual reaction mechanism, and how we're going to actually remove the other variants that may be produced on the side. And as they say here, the orthopara ratio is of interest because isolating pure disubstitute products is of interest. Assuming the attack at the 2 positions occurs purely statistical, their ratio is predicted to be 2 to 1 of ortho to para, because there are 2 orthocarbon and only 1 para. So right here, when they say 2 bromo nitrobenzene, that means that here could be the nitro. Here could also be it in the ortho, right? But para only has 1 location. But in this instance, it neglects the possibility of the steric bulk and the inductive electronic withdrawing effect of the bromine. So this is what I was trying to harp on at the start of the concept here, is that it is electron withdrawing of bromine might inhibit the approach of the electrophile to the ortho relative to para by determining the relative amounts of 19 and 20 produced. I believe that they mean here, one of these is 19, 120. You'll be able to evaluate this hypothesis. Another product may result if further nitration occurs, because nitration can kind of continue to occur if you let a reaction go for too long. Considering the direct effects of the bromo and nitro substituents leads to the prediction that the major product from both isomers would be 1-bromo 2,4-dinitrobenzene and 25. Let me see, where are they talking about these? Okay, now they're just placing numbers without actually having any reference, so that's great. Regardless, possible formation of 1-bromo 2,6-dinitrobenzene, which would be the 2 ortho positions, versus in this one would in this case be, it would be right here, and then additionally at the 4 position would be para. So that's what they're saying here, and possibly on Google afterwards we can take a look at those drawing. And going forward, they say the possible formation of the ortho is less likely because of steric and inductive effects of the bromo. So steric's highly affected as well as inductive effects from bromine itself. Then we can actually minimize dinitration by performing reactions at temperatures below 60. So remember that temperature and catalyst can be the driving force of reactions, and that the activation energy, like the previous heterocyclic reaction you're talking about from the last lesson, can actually affect the quantity of nitration and the location of nitration in this instance. So it suppresses it because the strongly deactivating nitro substituent raises the activation energy for the nitration. So as it goes forward, it's reducing the desire to push forward and creating a higher energy barrier that it cannot cross. And it can also precipitate out. And that's going to be part of the procedure that we're going to be tackling. For that way we can obtain our precipitate and stop the reaction in its steps. So going forward, the obstacle for isolating it is separating it from the 2. So you see here 4 bromonitro versus 2 bromonitro. We're going to be having to kind of battle here these 2, because these 2 will be both abundant in our reaction. And as we spoke of prior, the attack on the meta position is not as favored due to the bromine being an orthopara director. So going forward, this difference is dramatically demonstrated by the relative solubilities in ethanol, partially irrelevant, but the main concept that we want to say here is that the ortho isomer is very soluble, but the para isomer is only slightly soluble. In this case, only 1.2 grams per 100 milliliters can be dissolved. And going forward, we can understand the ideas of here. If we were to take a mixture of products and dissolve it in the hot 95% ethanol, then the solution cools, we can perform a sort of recrystallization method in a sense. So a less soluble para can selectively crystallize and isolate by filtration. And then concentration allows the isolation of second crop off on the side. Then going forward, it is commonly possible to induce the crystallization of the more soluble component. And here they're saying that the low melting point means that this isomer is difficult to crystallize. So that means that isolating this isomer involves column chromatography, which is not relative to what we are actually discussing. It is a separate portion that they like to throw in there to confuse you. So mainly focus on what we have provided from the procedure and what our actual action is, because for some reason these lab notebooks, they like to run off on tangents. So make sure when you're reading through them to stay focused on what we are performing and not what they are performing today. So we have our concentration here of nitric acid, sulfuric acid added there. Then approximately add in 0.5 milliliters stirred in. Okay, so the main thing I want to get to here is the critical actions. We don't want to have the temperature exceed 50 to 55 degrees Celsius, because like we know, that will contribute to dinitration. We do not want that, okay? After the addition is complete and it's subsided, the heat of the stirred mixture is going to be near but below 60 degrees Celsius, so we would want to watch that. Then we cool it and then pour it carefully and stir it into 40 milliliters of cold water. So right here, we're performing vacuum filtration afterwards because we're using cool water to precipitate out most of our product. And then we wash the filter with cold water until it's neutral to wash out any of the excess acid. So in the question here for the ortho-para, that would be crystallized. So what they say up here is that the less soluble para isomer, so what happens is, so both the ortho and para, they're taken in where we heat it in ethanol, right? Then the ortho is very soluble, right? The para is slightly soluble. So what we would do is we heat both together. Okay, we have our ortho and para. We know that because it came out, it precipitated firstly. We redissolve it into the hot ethanol. okay? Then the less soluble para isomer will crystal out once we slowly cool down. So the idea is to keep the ortho isomer in the hot ethanol or in the cold ethanol once it's cooled down. And then the para isomer is going to selectively crystallize out. So make sure to refer to this part right here, that the less soluble para isomer will selectively crystallize from the solution, and then we filter it once more. So that's the big one here, is that after the filter. So this is the part here that we would have to take 2 days, because they would want you to get rid of all of the water from it, because we're going to be utilizing high concentration of ethanol, and any sort of water will kind of throw off that dilution and create a azeotrope that we can't reduce. So with that being said here, okay, we take the crude product and 95% ethanol, right? We take our crude filter cake is what they're calling it, your crude product, your orthopara, it's there. You put it into your ethanol, you heat it very, very hot, stir it all in there, then allow the residual solution to cool down to room temperature. Then once it's cool, you put it over into an ice bath, and we'll see that in the video. Then you can isolate the crystalline product by vacuum filtration, and then your ortho will be left in the ethanol because it's still very soluble at room temp, or even cold. And then we can wash it with some of the ice cold ethanol to rinse off any of the ortho that may be trapped in your crystals. Then, finally here, concentrate the mother liquors to a volume by simple distillation. And then we're going to be taking that over, and then you can use rotovap or other techniques to concentrate it down and allow the residual solution to cool. And that would have a second crop of the 4-bromo, which would be the para bromonitrobenzene. And then after that, they would isolate a vacuum and air dry in a separate vial. But again, we're going to go through this in the video here shortly. Make sure in your machines that you have an oven as part of it. They're talking about IR spectra, so make sure that you have your IR machine there added as well. Then also melting point, make sure your melting point machine is added as well. And then let me switch over to here to watch the video, because they are also talking here as well to further concentrate the mother liquors from a second crop. That would result in a crude 2-bromo nitrobenzene. And this is also would be separate situation here, because you have your distillation. You can have a crop of 4-bromo nitrobenzene, which would be the para, but then also you can have the mother liquor here aside. That would be a crude 2-bromo, the ortho version of the nitrobenzene. So let's watch the video so that way you can actually see the good example of that happening. And I do greatly recommend to watch it again after our class period if you haven't already, so that way that you can get clarifications, because there is a lot of in-betweens with regards to is it para, ortho, etc. So let me switch over here. And here, great. So this is a great thing, because then we have our mechanism here we talk about, okay? This is nitric acid, okay? And take note, this is going to be how you're going to be doing your mechanism for your lab notebook. So nitric acid, the hydroxyl group here, takes a proton from sulfuric acid, okay? The electrons move to the oxygen. Then you're left here with your protonated nitric acid, and then you see here, this looks like water on the side, HOH, okay? This is a common mechanism in chemistry for water to leave the system. So the electrons from your oxygen can move down to create a double bond to nitrogen, and water can leave your system to create the nitronium ion, okay? You have nitronium and water as a side product. Here is a great part of the bromine resonating onto your benzene ring, so that way that you have your nucleophile, the arene nucleophile, okay? So these electrons, ortho to your bromine, they're going to attack the nitronium ion here. And then the electrons on the double bond are going to move over to the oxygen in order to create your nitro group, okay? Then, so here he's kind of behind. I spoke in front of him. The base, whether that be water or, like they said, a bisulfate, can come in and take the proton, donating the electrons over to create your arene ring again. And then finally, the bromine's double bond can come back up to donate the electrons back over, and you finally have your stable ortho nitro group. And then secondly, let's see if they go over to the para. The para product, however, would be the same thing, but the resonation down over to the para position instead of just resonating over to the ortho position, okay? So the same mechanism happens. The para position is now the nucleophilic electrons attacking the nitro or the nitronium and then allowing the base to abstract the proton adjacent to the nitro group, leaving you with your para nitrobromine, your para nitro bromobenzene instead of your ortho nitro bromobenzene. So then, now that we've gone forward and we've already discussed the mechanism, you can review it again watching this video or on the video here that I'm going to post. We take our sulfuric acid. I'm going to kind of skip through because it's very, very simple, and you can watch that part. They take a lot of time and safety because it's acid. You want to be careful. You take your nitric acid, put them together, okay? Then you have your bromobenzene. You add it in there, dropwise. You can see some of the kind of heat is producing some of the vapors. And they don't even heat it up at first. They just let it go because you don't want to go over 60 degrees Celsius, right? Because then you can get dinitration, and that would be bad. So you can see commonly here, most of the time, like if you're doing distillation, you would have your thermometer up. They have it down because they want to control the reaction. They control the temperature of the still pot. So it goes down into there. They're watching the temperature near 25. They're good to go. They're probably going to add in a little heat as they add in more of the dibromo. Now it's going up to 30. Skipping forward because we don't really need to be too critical on watching, but yeah, so now they're going to, what they're doing, the reason that they're going to be cooling it down is to precipitate out the nitro bromobenzene. The reason they're precipitating out is because, like they said, the starting material is soluble in the acids. However, it is insoluble once we've nitrated it. So that's perfect for us because we want our precipitate to come out as our product of the ortho and para. Okay, so we're going forward, skipping over here. And I believe that they might have cooled it down there because they were trying to control the temperature, make sure it didn't boil too hot, because it does get hot. So we want to hold it back. So here's part 2. We finally have finished our reaction. And you could listen to the audio separately because I'm kind of just skipping through here so that everyone can see what we're tackling. So firstly, we're removing the stir bar so that way that we can have an easier access of our filtration, and we're going to put that over in there anyways. Then we're going to pour it over into the ice cold water. I'm going to put some water in there to get out the caking. As you can see, it kind of cakes on there, but that's good. That's going to be our product, and that's what we want to hold on to. Skipping forward. We're going to get to the filtration here. Okay, cool. So you can see at the bottom, very clear. Liquids just going through. We don't see any of our products slipping through. We're going to use a lot of water to clean off the acid, to get rid of all that acid that's on top, because we were running the reaction in a lot of acid. Very strong and can be dangerous, so we need to rinse it off. So now it is highly insoluble because it's an aromatic ring. The bromine, nitrogen, or the nitro group, those are slightly polar, but not polar enough to make it water soluble. That aromatic group is very nonpolar. So they wash, they wash, they wash. Then they have their cake. Now we have more washing, lots of washing. Tons and tons and tons of washing to neutralize. And then, so this is the part of testing with the pH strip to make sure that the solution is no longer acidic. So we would continuously test until we see like closer to green, the neutral color of the paper, and then more red is acidic. Like you see, that's extremely like pink red, like super red, bad, acidic. We don't want it to be like that. We want it to be more green, more neutral, and then blue would be basic, in case you don't remember off the top of your head. Okay, so here, filtrate acidic. This is the first after wash, still red. Second wash, slightly red. Now we wash it again, and we're going to be washing and washing and lots of washing. So you can see why this takes 2 days, because so much washing. And then finally we'll skip over to here. And this is the most important part. Let me repause it if I can. Well, I can't really pause it very well because it's going to kind of make it stilted. But so this is the part here. Ortho bromobenzene is going to be polar and soluble at 95% ethanol. However, para nitrobromobenzene is nonpolar, and this is going to precipitate in cool ethanol. But we want to recrystallize, so we heat it up, we get everything into the solution, the ethanol, and it completely dissolves hot, and then whenever it cools out, then it'll come out nicely with crystalline, less impure solution. So coming over here, I'm going to kind of skip through. This is going to be mixing it in and heating it up with our ethanol like they showed on the board. Okay. Now we cool down to room temperature for a little bit. Now we're going to be we put it over into the ice. So now that they've had it over in the ice, let me see, they kind of skipped it. There it is. Okay, so it was in the ice. Once it's completely precipitated out nicely, then we're going to take it over into our filtration setup again, right? Because then we can filter off our nice precipitate, the para, leaving the polar soluble ortho nitrobromobenzene. This is the second vacuum filtration. So this is to separate the two isomers. So first they wet it to make sure that then nothing falls through the filter. We're going to save our product, right? We wash it through. You can see the liquid is colored. The reason it's colored is because that's going to be our soluble that's going to be our soluble ortho nitrobromobenzene. Our nonpolar insoluble para-nitrobenzene is going to be precipitated out. So make sure you just remember, para is nonpolar. The ortho is polar. So those two will be separated easily here. So now we've washed it through. We're going to get the rest of it out. We're going to add in ice cold ethanol. And then the simple distillation of mother liquors is to allow you to distill over your ortho in that case. So here's your para. We don't have to distill it here because we've already precipitated it, right? So the ortho that is polar is in the mother liquor, which is the ethanol. It's just sitting there. It's dissolved into the ethanol. So we need to remove the ethanol. So here's the oven. Make sure to have that in your instruments. The para insoluble in ethanol is going to be the precipitate, and all we got to do is just rinse it with ethanol and then let it dry in the oven, and we're good to go. Now we have our ortho in ethanol. And then we have our simple distillation setup. I'm not going to explain this to you. Make sure to have your heating mantle within your instruments and your glassware for simple distillation in your apparatus. Meanwhile, this has been dried. We weigh out our product. And then finally, since we've boiled off all of our ethanol, we're left with our pure, nice orthobromo nitrobenzene. And you can see it's very colored, very dark colored because of the bromine and nitro. Very dark here, okay? So finally, you can calculate here by you remove the mass of your filter paper from the mass of your product to get the para. The way to measure your ortho is to take the volume of your product and then, okay, this is critical. If you don't know how to use density, this is how you do it, okay? You have your volume of your product. The density is directly related to grams per milliliter. So what would we do? We would multiply 1.2 times the density, 1.719 grams per milliliter to get grams of your ortho product. So the the volume is relative to the weight by the density. Separately, you can weigh it on the scale if you were to pour it into a tared vial or flask or something. But in this case, you can just take the milliliters, multiply it by the density, and then boom, you have your total weight. And then finally, of course, calculate your percent yield and your theoretical yield. You'll have to calculate from your living reagents. So that's going to be the walkthrough on that. And if you need to tackle any of those in a separate system, then I would recommend to watch it on a separate video, or rewatch the videos if you need to. For the data, let me open up here. Make sure to look through here and let me know if your data is not here. I have opened the separate. One moment. Let me pause the share really quick. So we had Hannah, James, and Lucy, and yours was not on there last time. Let me check here. So Hannah, James, Lucy, I'm not seeing any of y'all. So I'm going to add in the data. Oh, wait, this is the Diels Alder. Hold on. This is not the correct data. I'm going to have to contact Dr. Rastogi to get the correct data because here it says the nitration, but this is Diels Alder. Wait. No, this is the correct. Okay, ignore this at the top where it says the Diels Alder reaction because this is the nitration data. It tells you your bromobenzene, your density, your concentration. I'm gonna edit this to add in the three of you for your data, and these are gonna be the what you need to utilize. Just please ignore the Diels Alder part. He accidentally left that there. And then once you've gone forward to analyze your data, make sure there is a second part. Here is your IR spectra. Okay, everyone needs to analyze this. You need to say which one is which. Assign it firstly for 2-nitrobromobenzene and 4-nitrobromobenzene. Assign the peaks. Make sure that you know which peaks are which. Where would you find a nitro group? Where would you find aromatic peak, bromine group? And then down here, you need to say which one is 2-bromo and which are 2-nitro and which one's 4-nitro. You need to assign it to both of these. And then you need to also assign the protons. Make sure to assign the protons to each of them. So that way you get full credit for your data analysis. Let me double check really quick. I believe he said also that there is no post lab here. But I want to make sure that I'm safe than sorry for y'all. So here, yes. So work very well on formatting. Make sure to analyze your data analysis and perform it. That'll be the only post lab. There is no post lab down here, okay? So the only thing there is data analysis and then the IR and NMR spectra analysis, okay? There's no post lab questions for this experiment. So next lab experiment when we meet up, we are going to be discussing the polymerization of nylon 610. And additionally, on here, yes, the polymerization of nylon 610, be prepared next Tuesday for that. Additionally, in discussions, remember, of course, that we need to be performing the HOLA chem discussion here sooner than later, and be thinking about your poster so that way that you'll be prepared for it being due the day after the final. Otherwise, this is going to be the end of the recording, and we're going to open up the Q&A section. Thank you for watching if you're watching this on YouTube.